Hello, everyone. Greetings and a warm welcome. Thank you for joining us today at the kickoff of this Climate Cafe series. Can everyone hear me okay? Okay, good. My name is Amy Clement, and I'm a professor here at the Rosenstiel School in the Department of Atmospheric Science. In my lab, we look at climate change around the world, past, present, and future, and also what it means for Miami and South Florida. This is the first of many Zoominar lunchtime conversations with faculty and graduate students. Our goal is to inform you about the many different aspects of climate science that are happening here at the Rosenstiel School and how our research activities are used to help inform policy while we train the next generation of climate scientists. Today's topic is climate science in the age of COVID. Before we get started, I wanted to just mention that we'll have a Q&A at the end of the speakers. So in the meantime, please feel free to send your questions during the program in the chat feature of the Zoom. Our Q&A moderator will be gathering the questions, so if you have a specific question for specific speakers, send it over sooner rather than later. Now I'm going to share my screen and show you where we get to do our work. Can everyone see this? Yes? So this is our beautiful school located on Virginia Key, right off the shores of Miami. It's uniquely positioned at the crossroads of tropical meteorology and hurricanes, as well as climatically important oceanographic processes like the Gulf Stream. Our location is ground zero in Miami for observing and studying the various aspects of and impacts of climate processes, physical, biological, societal impacts that continue to evolve on a daily basis. Directly across the street from our campus, which you can see over here on the right-hand side of the picture, is NOAA's Atlantic Oceanographic and Meteorological Lab and the Southeast Fisheries Science Center. Our school hosts a NOAA Cooperative Institute for Marine and Atmospheric Studies, which is one of 16 institutes in the country, and we're fortunate to have the director of that institute, Ben Kirtman, here on the call. You'll be hearing from him in a bit later. At our school, we have undergrad, professional master's, and PhD programs, and our faculty provide first-class instruction and research opportunities for all of these students. So without further ado, we're going to start hearing from these wonderful students of ours, and I'm going to turn it over now to a PhD student in her second year, Sisam Shrestha, who's going to be talking about record-breaking weather and climate in 2020. Thanks again for coming, and we'll see you at the Q&A.
Okay. Good morning, everyone. My name is Sisam Shrestha. I'm a second-year PhD student working with Dr. Brian Soden in the Atmospheric Science Department here at the Rosenstiel School. And today I'll be talking about extreme weather events that we've experienced in 2020 so far. So first up, we have the Australian bushfire, which was a continuation from 2019. The bushfire that lasted for around 8 months burned 20% of Australia's forest, and it caused a huge damage not only on land, but also on our atmosphere as measured by different NASA satellites. So NASA's Calypso satellite on January measured a smoke plume top at 25 kilometers, which is the highest wildfire-caused plume ever tracked by this particular satellite. This figure here by the NASA's microwave limb sounder on NASA's Aurora satellite shows the amount of carbon monoxide that the bushfire injected into the stratosphere. This was the highest amount of carbon monoxide injected into the stratosphere that the microwave limb sounder detected in its 15-year mission. This Joey over here was rescued from one of those fires, and according to a study initiated by the World Wildlife Fund, he was one of the 3 billion animals estimated to be in path of this 2019 to 2020 bushfire season. Next up, we have the Siberian heat wave, which was ongoing pretty much for the first half of this year, from January to June. The figure here shows the Batagaiga crater that has been growing since the beginning of this year due to increased heat. And this year we recorded a temperature of 104 Fahrenheit, which is the highest temperature recorded inside the Arctic Circle till date. The Siberian heat wave also initiated a bunch of Arctic wildfires before the normal Siberian fire season. And this year we registered a Siberian Arctic fire at the highest northernmost latitude at 72.723 degree north. These wildfires in June burned around. This wildfire in June burned around 1.15 million hectares of land, which released 56 megatons of carbon dioxide into the atmosphere. That's roughly equal to the annual carbon dioxide released by industrialized nations like Switzerland and Norway. This figure here by CAMS shows the June carbon monoxide values compared to other years. As you can see, pretty much everywhere in the Northern Hemisphere, the carbon monoxide values are blue or yellow, suggesting that it was either at or below the average values. However, there is this huge spike in carbon monoxide in Siberia that is shown here with the red shading, which also happens to coincide with these locations of Siberian blaze. This year, we also got to experience one of our biggest Saharan dust outbreak. Saharan dust outbreaks are a yearly phenomena where winds pick up dust particles from the Sahara Desert and transport it across the Atlantic. Here in Miami, we get to feel its effect every now and then. But this year, it managed to travel 8,000 kilometers and affect places like New Orleans, Houston, and even Ohio. This figure here by Professor Prakita Zudema here at the Rosenstiel School shows the exact moment where the Saharan dust interacted with one of the thunderstorms here in Miami. According to NOAA's AOML lab, this particular outbreak was around 70% bigger than your average Saharan dust outbreak, making it the dustiest outbreak on record. This figure here by Michael Lowry using MODIS data shows the aerosol optical depth since 2003 to 2020. Aerosol optical depth in this case is basically how thick the dust layer is. So as you can see in June 20 in the upper right-hand corner, the aerosol optical depth was 1.66, higher than any other measured till date. In terms of smoke plume top height, dust plume top height, it was 6 to 7 kilometers right off the North African coast, which is way higher than your normal Saharan dust outbreak. Looking at some local records, Miami had its very own set of record-breaking weather events this year. We experienced our hottest first third of the year, as shown by this graph here by Brian McNulty, who is a senior research associate at the Rosenstiel School. We had a mean January to April temperature of 75.9 Fahrenheit, and the probability of experiencing a temperature of that degree or hotter than that is less than 1%. We also had one of our wettest Mays on record with precipitation of 18.89 inches. And we experienced our hottest month on record, also our hottest July, of 85.9 Fahrenheit, which was 0.2 Fahrenheit hotter than the 2017 August. Moving towards the poles, the Antarctic also recorded its hottest temperature of 18.4 degrees Celsius, which, if verified by the World Meteorological Organization, will be the highest temperature ever recorded inside the Antarctic continent. On the other side of the globe, the Arctic had its lowest ozone concentration with 205 Dobson unit. Dobson unit is basically how much the ozone would be if it were to be compressed to a really thin slab. And as for the sea ice extent, this year we've been having one of the lowest sea ice extents in the Arctic than average. For the month of June, we had Arctic sea ice 10.1% lower than the June average, which puts it as the third smallest June sea ice extent on record ever since satellite data began in 1979. Now, the Earth as a whole had some very interesting record-breaking events in these 7 months. We had our hottest January with temperatures 1.14 degrees Celsius above the January average. We also had our one of the hottest Mays with temperatures 0.95 degrees Celsius above the average. The only other time we had a May this hot was on 2016 when we had a huge ENSO event. Our February, March, and April were the second hottest on record for their respective month. And finally, looking at the ocean as shown by this graph by Chris Karnauskas, the 18-degree isotherm, the red line this year, is farther north than normal for this time of the year, which was supposed to be around Cape Cod, but now is past Bailey Island in Maine. So this has implications not only on the marine ecosystem, but also on people who depend on marine ecosystem for their livelihoods. And with that, I'd like to end my short presentation on extreme weathers we've experienced in 2020 so far. If you have any questions, please put it on the chat section and I'll try my best to answer it at the end of this talk today. Also, you can always reach out to me through email provided here. And now I'd like to hand it over to Marybeth.
Thank you, Sisam. So as we can see, the need for weather and climate research is more important than ever. And so I have the difficult task of trying to summarize the climate research ongoing by students here at the Rosenstiel School. So my name is Marybeth Arcodia. I'm a fifth-year PhD student in Ben Kirtman's lab in the Atmospheric Science Department. Today, we want to highlight the large number of research questions and topics being researched here by climate students at the Rosenstiel School. So first up, we have Amy Clement's group. You recognize Amy from giving our introduction. Her group focuses on climate modeling and mechanisms of past, present, and future climate change. First up, we have Jeremy Clavins, who's a fifth-year PhD student studying Atlantic climate variability. Right now, Jeremy is using observations and climate models to try to understand how Florida rainfall will change during our fall flooding season in the future. The picture on the left is a sunny day flood from October 2019. You can imagine that if it was a rainy day, things might have been a lot worse. In his most recent paper, Jeremy shows that when the Atlantic Ocean is warmer than average, we have a wetter than average late summer here in Florida. And this relationship appears to be related to human-caused changes in the climate system. We can see that in the map on the right. The blue areas are wetter when human-caused changes in Atlantic Ocean temperatures lead to warming. In the near future, we expect the oceans to continue to warm, and therefore Florida rainfall during our flooding season may increase. Tyler Fenske's in his third year. His research focuses on how climate patterns in the North Atlantic and Pacific Oceans cause specific types of weather in North America and Europe. Predicting these climate patterns can help us predict weather in populated regions better. If the two oceans are related, predicting conditions in one allows for prediction of conditions in the other. However, the results are suggesting the two are not related. To highlight some of our undergraduate work, here we have Sydney Kramer, who recently graduated from undergrad. Her research shows that large ensemble climate models and observations suggest that humans have been causing an increased correlation between lower vertical wind shear and warmer sea surface temperatures in the last century, especially since 1950. With the help of harmful human activity, conditions in the Atlantic have been and will continue to be more favorable for hurricanes to form and become more severe. Stronger hurricanes can cause more danger to vulnerable coastal communities like Miami and create more costly structural damage. And last in Amy's group, we have Oakland Keefe. For the past year, Oakland has been researching hyper-local urban heat islands in Miami-Dade County. In 2019, 0 heat advisories were issued by the forecasting offices. But according to Keefe's research, at least 32 heat advisories should have been issued based on local heat indices. These results are important because they show that areas of Miami-Dade County are much hotter than what weather stations are reporting. Therefore, weather sites using data from airports are not providing accurate or safe data for their customers. Next up, we have Brian Soden's group, and Brian's group focuses on understanding climate feedback processes, the water cycle, and the response of extreme weather events to global warming. Boson Zhang is in his 5th year. He studies how positive cloud and water vapor feedbacks are coincident with the convective envelope of the MJO. Cloud changes induce the largest radiative perturbations associated with the MJO. Stronger radiative heating due to water vapor and clouds helps the Madden-Julian oscillation survive the barrier effect of the maritime continent here, leading to further eastward propagation. Bo works on tracking individual MJO events and responses of radiative feedback variables such as temperature and water vapor. Halja is in his 3rd year. Radiative forcing is a fundamental metric for measuring the extent to which human activities, such as the emissions of greenhouse gases and aerosols, and natural events like volcanic eruptions, perturb the Earth's energy balance. This perturbation initiates all other changes of the climate in response to external forcings. 2 feedbacks highlighted here are the combination of lapse rate and water vapor and cloud feedbacks. Next, we have Sisam, who you heard from last about the extreme weather events, and she's a 2nd-year PhD student working for Brian Soden. She is currently studying water vapor trends in the atmosphere using different scenarios from the highly complex climate model intercomparison project models. Since water vapor traps radiation emitted by the Earth's surface and then re-emits it back towards the surface, it can contribute to additional heating. Computing how water vapors change through the years in each model and comparing them with satellite observations can help us fine-tune the models for better future predictions and study the contribution of water vapor in a warming world. And lastly, we have Ben Kirtman's group, and Ben will be speaking after me. His group focuses on climate predictability and prediction, weather-climate interactions, and high-resolution ocean modeling. First up, we have Brianna Zavadoff, who recently graduated with her PhD. Her research focuses on the dynamics behind the intra-basin variability of summertime North Atlantic Rossby wave breaking. This sounds like a jumble, but it's really just characterized by the folding of long planetary waves known as Rossby waves in the upper atmosphere. Studies have shown that fewer tropical cyclones form during years which Rossby wave breaking occurs more frequently in the western North Atlantic. Brianna found that the alternating phases of the Pacific Decadal Oscillation were responsible for this variability. She hopes that her research will aid in long to medium range predictability and forecasting of North Atlantic tropical cyclones. Whoops. Simge Bilgen is a 5th-year student, and unlike the rapid observed warming in the Arctic, the Southern Ocean exhibited a notable multi-decadal cooling trend. These negative SST trends in the Southern Ocean are at odds with greenhouse gas-induced warming over much of the world's oceans in recent decades. Understanding the climate of Southern oceans, recent trends in climate models has played a role in helping the climate community interpret the structure of recent climate change. Next is my research. I'm a 5th-year PhD student. I study climate dynamics and predictability using observations and a variety of climate models. The work shown here can help explain why California received significantly less rainfall than predicted during the 2015 El Niño event, while massive flooding occurred in the Mississippi River Basin. Although the sources of changes in rainfall patterns are coming from thousands of miles away in the tropical Indian and Pacific Oceans, our study shows just how connected the tropics and the United States can be and can lead to more confidence in our weather and climate forecasts. Kayla is a fourth year who studies atmospheric blocking, which is sort of like traffic jams in the atmosphere that divert large-scale flow for prolonged periods of time. Atmospheric blocking is one of the culprits that has contributed to extremely high temperatures and increased amount of wildfires that have been seen in Siberia this year, as Sisam mentioned earlier. The work here goes beyond individual events considers how the changes in atmospheric flow caused by these blocks can influence sea surface temperatures at longer terms. Understanding this interaction and resulting ocean temperatures can help us better predict when larger impact events, such as El Nino, may or may not occur. Kelsey Malloy is a fourth-year PhD candidate, and she'll also be helping in our Q&A session later. She studies predictability of summer rainfall in the plains by understanding moisture transport in this region. In the summer, there is a conveyor belt of moisture between the Gulf of Mexico and the plains that triggers rainfalls and storms, as you can see in the animation. Kelsey hopes that by understanding global influences on that surge of moisture transport, we can predict that rainfall. She's researched linkages between that moisture transport and sea surface temperatures, monsoon systems, and the Bermuda High over the Atlantic. Karen Papazian is a second-year PhD student. She is currently finalizing her research plan, which will focus on the impacts of climate change on the Intertropical Convergence Zone. This zone, called the ITCZ, is a region near the equator where the trade winds from the northern hemisphere and southern hemisphere converge. The ITCZ is known to have strong convective activity, meaning strong rainfall. Knowing the location and strength of the ITCZ during a changing climate will help us understand the impacts of the rainfall and wind shifts on affected communities and ecosystems. Lev Lynée is a second year, and he's co-advised by Ben Kirtman and Greg Foltz at NOAA across the street, as Amy pointed out, at the Atlantic Oceanographic and Meteorological Laboratory. He is currently in the initial phases of his research to understand the role that ocean stratification has on tropical cyclone intensity changes. Ocean stratification is how the different properties of the ocean change with depth. Currently, intensity is one of the least improved forecasts for hurricanes. Hurricanes, especially the slower moving ones, cause the temperatures at the sea surface to cool by bringing deeper waters to the surface. Overall, Lev hopes to relate this back to improving intensity forecasts to better prepare people for landfalling storms ahead of time, particularly important to us here in South Florida. Victoria Schoenwald is a second year. She is beginning to study how sea level rise and coastal flooding are changing along the east coast of the United States. Instead of looking at how the coastline will be affected by rising seas decades out, she wants to see which areas will be most affected in the coming days to year. Victoria hopes to predict where hot spots of sea level rise will move to in order to help with coastal planning. Again, extremely important for us, especially here in Miami. Sam Kramer recently graduated with her PhD and was co-advised by Ben Kirtman and Paquita Zaidama. We breathe in Saharan dust each summer in Miami. Saharan dust is the largest contributor to our aerosol environment and therefore important for air quality, even though it's a natural pollutant. While at the Rosenstiel School, Sam studied the atmospheric conditions like wind and pressure on weather and climate scales, which bring the most Saharan dust to our city, as we saw just a few weeks ago. With a better understanding of how our atmosphere transports dust to Miami, we can better predict when it will arrive and how much may arrive further in advance. We also want to highlight some of our interdisciplinary climate research. Anne Barkley is a fifth-year PhD student studying atmospheric chemistry in Professor Gaston's lab. Her dissertation is focused on characterizing the size and chemical composition of aerosols from Africa that get transported to South America. African dust is transported to the Amazon over the course of about 5 to 7 days. Nutrients associated with this dust, including iron and phosphorus, get deposited in the soil. Just like fertilizing a garden, these nutrients fertilize the Amazon and promote plant growth, which in turn draws carbon dioxide out of the atmosphere. Good news. And recent research shows that nutrients associated with fires, both man-made and natural, also contribute nutrients to the Amazon as well. And lastly, we have Caroline Cron, who's a second-year PhD student in the Environmental Science and Policy program at the Abess Center, working with Dr. Catherine Mock. She is interested in how flooding impacts societies and how policies can be designed and implemented to manage flood risk. One such policy would be managed retreat, which is the purposeful relocation of people and assets out of high flood risk areas. One way to manage retreat is through voluntary property buyouts. We can learn from past buyout programs to improve the process and outcomes going forward. We will be discussing much more of this climate and society interdisciplinary research at the third part in our Climate Cafe Zoominar series on September 2nd, so make sure to come back for that one. So as you can see, this was just a quick overview of some of the exciting research being conducted here at the Rosenstiel School. As Amy stated earlier, in a rapidly changing world, it's now more important than ever that we understand our climate system and make confident predictions for the next few days to years to come. The work being done here at the Rosenstiel helps to inform policy and decision makers and help prepare for the long-term impacts of climate change. Now I will pass it over to Ben Kirtman, who will be discussing all of this climate research in our current times.
Thanks, Marybeth. And I also wanted just to take a moment to thank Marybeth, Deanna Udell, and Sisam for organizing this and coordinating this and the opportunity to speak. I really do appreciate that. So in just the next 10 minutes or so, I'm just going to talk about one specific aspect of climate change in the age of COVID, and that's really focusing on CO2 emissions and CO2 concentrations. And I should say I'm a professor in the Department of Atmospheric Sciences, and I'm also involved with the Cooperative Institute for Marine and Atmospheric Studies, and I'm also involved with the Institute for Data Science and Computing here at the University of Miami. So just as a quick outline, maybe you've seen some of these headlines, you know, CO2 levels hit record highs despite emissions dip from coronavirus. So I just want to kind of touch on that and explain why that might be the case. And also, you know, try to understand why we wouldn't expect necessarily a temperature response from what we've seen to date. And then the second thing I do want to talk about, you know, when I think about climate change research in the age of COVID, there's also how do we conduct our research in this much less face-to-face world. And so I do want to talk a little bit about some of the field programs and servicing of in situ observing systems and how that influences the research we do and how some of that is actually going forward. And then the last thing, I just want to show one highlight results from the recent hurricane that we had in the area and some tantalizing results from some of our prediction experiments trying to capture that 3 to 4 weeks in advance, which is quite remarkable. So just to get you up to speed and just to remind you that emissions, of course, are different than concentrations. So if emissions continue to increase, you would always expect concentrations to continue to increase. So one way to think about this is a little bit like a bathtub with the spigot on. So the spigot is the water flowing in, that's the emissions, and then the drain is how fast the CO2 comes out of the atmosphere, and the concentration is the level of water in the bathtub. Now, the thing about the drain with CO2 is it's a very, very slow drain. So if you imagine we have 400 parts per million by volume of CO2, and we know that the half-life of CO2 is on the order of, say, 2,000 years, it would take about 2,000 years for the bathtub to drain from 400 parts per million by volume to 200 parts per million by 200 parts per million by volume. So that drain is pretty slow, and that's primarily the reason. That's a good reason why we don't actually see a very big change in the concentrations over the few months that we've seen big reductions in emissions. Okay, so just to, again, this is from 2018, just so you get a picture of the playing field. These are annual carbon emissions from various countries around the world measured in tons per year. In this particular statistic, the US and China are the largest emitters, and Canada and Russia are close seconds, and China's in the mix. And India's in the mix. If you did this per capita, it would change quite a bit. US and Canada would sort of be in the top emitters if you did it by per capita. And then I just want to show you a short movie. This movie is starting in January 2020. So it's looking at emissions, not concentrations now. It's just looking at emissions. And the deeper the blues, or the brighter the blues, I should say. I always have trouble with my colors. The brighter the blues indicate the larger reductions in emissions. And what you'll notice is this nice pattern. You can tell when the outbreak happens in China first, and then happens in the US later, and when economies start to reopen, because that's closely connected to emissions. So it's a nice little video. And so you can see we're going through January, and then you can see China shut down, and then the US emissions started to significantly decrease as you go into February. And then you can see particular states with a hard shutdown, and then you see that in Russia, and then you see China has come back. Emissions have gone back up because they opened up, and slowly the US started to open up. And this went through May 20. And so you can see that nice little reduction and oscillation, and the net increase is decrease over this few month period, basically from January through the present, is something on the order of 8% reduction in emissions. If we look at that a little bit more carefully, on the left-hand side, it's looking at global emissions. The first panel is looking at just the time series of daily fossil fuel emissions going up to the present. And so you can see from 1970 to the present, you see that really rapid, that fall off, that rapid drop in emissions that happened beginning in very late 2019 and early 2020. And then this is just sort of zooming in that January through May period. The right-hand panel in the left side is showing you that reduction that happened over that January to May period of 2020. Now the right-hand colored panels here, this is an interesting plot from my perspective, and it shows you the various sectors of economic sectors, if you will, where the reductions are coming from. And if you look at the surface transport and the aviation, you can really see how economic shutdown is intimately connected to fossil fuel emissions. You see this significant drop in surface transport and a significant drop in aviation. And then if you look at residential usage, emissions from residential use, you can see it's fairly flat. People still were using power, but they weren't driving their cars and they weren't flying in planes. That surface transport reduction is about cut the emissions from surface vehicles, personal transport vehicles, by half over that 4-year period, 4-month period. So that's pretty impressive, by half. Similarly with the aviation, about half. And so it gives you a sense that we could, if we came together and had some coherent policies worldwide about how to handle emissions, we could make significant reductions in emissions. And then this is just to show you perhaps somewhat disappointingly that those big reductions in emissions, we're really not seeing much of a signal in the actual concentrations that we're seeing in the atmosphere. So the left-hand panel here is showing you since 2016, right up and through the end of July, the CO2 concentrations that are captured from the Mauna Loa Observatory in Hawaii. And one thing to know about CO2 is it's a fairly well-mixed gas. So these Mauna Loa measurements are a pretty good estimate of where CO2 is in the whole atmosphere. And the red curve that goes up and down, that's sort of the seasonal cycle or annual cycle of the atmosphere. It's sort of breathing, winter, summer kind of breathing. The black curve is sort of smoothing that out, taking out that seasonal cycle, and just shows you the long-term trend. And so you can see that they're really, it's really hard to detect any kind of significant reduction in the CO2 concentrations in the atmosphere. And then, of course, the right-hand panel shows sort of a longer view of those CO2 concentrations in the atmosphere, and that steady increase, quite amazingly, going from 320 or slightly below 320 parts per million to well over 400 in just that 60-year period. And then just to give you an idea of how important, we really do need to think about this emissions problem in terms of what we can expect going forward in terms of how the climate system is going to evolve, what it's going to look like in terms of the temperature. And that this plot is just showing you, if we don't have any change in policies, what would be the warming response at 2100, and also what those emissions might look like. And then, under current policies that exist today, considerably less warming and considerably less carbon in the atmosphere than pledges and targets that are out there. The countries have made pledges to meet, and these are great. I mean, this is important stuff, but we have to recognize that even with existing pledges and targets, we're not going to get to that 2-degree equilibrium climate, or that 1.5 equilibrium climate that we believe is what's necessary in order to sustain the world that we enjoy. So there's some big challenges here in terms of emissions that we need to think aggressively about. Of course, I want to make a plug for the Cooperative Institute. We were recently awarded the Cooperative Institute, and this is part of what, how the University of Miami and the federal government collaborate in order to do things that the federal government can't necessarily do by itself. They need that collaboration to work with us. And of course, there's things the university can't do without the assistance of the federal government, and the Cooperative Institute is a great example of that. And I just want to show you one thing. Very recently, in the age of COVID, scientists from the federal government aren't able to participate in field campaigns, go out there and launch instruments. In this particular example, one of our Cooperative Institute scientists, and if you notice the little logo, that's the logo for the Cooperative Institute. These are Argo floats, about $100,000 each one of these floats. But one of our scientists teamed up with a group of folks in Puerto Rico, and you can see this, everyone's wearing masks. This is during COVID, and they launched several of these Argo floats in Puerto Rico in advance of that most recent hurricane. So that was data, we were able to collect data associated with that most recent hurricane that will ultimately be used to perhaps improve hurricane forecasts going forward into the future. And just, last plug, just to really say, this quote, we're really excited about the Cooperative Institute, and it's hosted by the University of Miami, but it's a collaboration, of course, with NOAA, the National Hurricane Center, obviously also, but also a lot of the academic institutions throughout the state. Then the last plot here is just something exciting that came up during the most recent hurricane. And on the right-hand side, this is just taken from a forecast from Sunday, August 2nd, and it just shows you the track of the storm, and then the precipitation estimates associated with the storm. So those were forecasts of precipitation estimates. And then on the left-hand side, this is a project that the University of Miami leads. It's called a subseasonal prediction experiment, or we just call it SubX. And it's just showing you what this multi-model, multi-institutional project is produced in terms of 3 to 4 weeks in advance of this current storm. And you can see during that 2 weeks, 3 to 4 weeks in advance, ending in the weeks ending in July 31st, you could see that the models overall were picking up that storm coming into Florida, and then in the next set of forecasts that it actually propagated up the eastern seaboard and into the mid-Atlantic states and beyond. So that's a success. I'll confess, we don't really know where that predictability came from, but that's the exciting part of participating in these real-time forecast projects opens up really interesting research questions that we're going to pursue. And then just the last slide, I just want to point out there's my pre-pandemic hairstyle, and then this is what seems to have happened to me in the age of COVID. That's where it stands. Thank you. And I will then pass it off to Lynée.
All right, my name is Lynée Turek-Hankins. I am a PhD student at the Abess Center for Ecosystem Science and Policy here at the University of Miami. I work with Dr. Catherine Mock, who leads the Climate Risks and Preparedness Research Group here at the Rosenstiel School. I'll be talking about research directions I'm pursuing with climate adaptation and environmental justice, and what this means in the current COVID-19 crisis. So the big question, how do we prepare for a changing climate? And in a lot of ways, the COVID-19 mirrors the climate crisis in that it is happening to us and we're learning about it as it is unfolding. And so as a climate scientist, we kind of think about answering this question through two different avenues. First is mitigation. And Dr. Kirtman covered this really well in that when we think about how we approach mitigation from the COVID-19 perspective, we can see how much as a society we've achieved reducing greenhouse gases. But if we want to avoid the significant impacts that are projected to come, we really need to push this even farther. And I'm not going to be covering this so much in my presentation. Instead, I'm going to be looking at the other side, which is adaptation. And again, following what Dr. Kirtman said, we are kind of at a point where impacts are really going to happen regardless of what we do. But the question is, how much of the impact are we going to have to deal with in the future based off of our greenhouse gas mitigations? And so adaptation is thinking about how do we start to make room and how do we prepare for these impacts that are likely to come? And we can think about approaching adaptation through this diagram, which is from the Intergovernmental Panel on Climate Change. And we can see that impacts stem from risk. And risk is a function of three different components: hazards, exposure, and vulnerability. Exposure you can think of as what or who is in the way of a hazard. So maybe that is our buildings, our bridges, our cars, but also our people. The hazard is the stressor that is being placed on the system. So maybe it is a wildfire, or perhaps it is a hurricane or a heat wave. And finally, vulnerability is that which makes certain populations more susceptible to the harms than other populations. And this one is actually a little bit more difficult to think about in that it is something that's really dynamic. And the other thing that's really tricky is vulnerability historically has been thought of as something that is much more in the negative, whereas what it doesn't consider is the unique adaptation capacities that exist within communities and the positives that they bring. So working from this traditional framework, we can think about vulnerability as components that may be spatially or temporally variable that, again, could make certain communities more susceptible to impacts. And the other thing that's really important is the fact that vulnerability is itself a function of the hazard. So for example, if we were to look at extreme heat, which is what I focus in my research, a community could be really vulnerable to the impacts of heat if it is really surrounded by asphalt or concrete and has a little vegetative cover. However, this might not necessarily be an issue for other hazards, like wildfire. And so again, we can see how important this relationship between vulnerability and hazards are. And going a little bit more into work that I'm currently kind of trying to push through is really thinking about, again, that component, which is vulnerability. And it's really messy to think about and measure because it is not something so simple as, is there a heat wave? Is there a building in the way? It's really nuanced. And what we found in our work is that it kind of breaks down into different components in terms of how people are currently thinking about and measuring which indicators signify communities that are more vulnerable to climate impacts than others. And this can be broken down into 4 groups shown here. There are environmental conditions. So for example, if a community is right next to a coal power plant, or if there is a lot of ground level ozone, that can make them much more vulnerable, especially when we think about traditional environmental justice problems, to a hazard. There are also economic conditions. So for example, are the communities relying on outdoor workers a lot and they might be more exposed? Is there an issue of poverty in that community? And another one is health. And health is obviously a function of environmental conditions and economic conditions, but it's often looked at separately from the other two, and that it's really easy to measure. And so that could be something like cardiovascular disease or asthma. And finally, again, we have something like demographics. And I mean, previous work has shown without a doubt that there are certain communities that are more impacted by climatic hazards, and that has to do with things like race, for example, which is tied to historic practices of redlining and other traditions that were built into these structures of our society. But it could also be something like age. For example, again, thinking about heat, we have the very young and the very old being much more impacted in terms of their health impacts. And so taking this understanding of vulnerability and then transferring it to our current situation, we could see how compound hazards, which are multiple hazards coming together in an instance, can change our understanding of which communities are most susceptible to impacts. And so in this graphic, I kind of have an example, which is we could have sea level rise from climate change, and then we could have a hurricane on top of that, and then we have the COVID-19 crisis. However, it's not just necessarily the COVID-19 crisis. It could be an environmental disaster, such as a spill or an explosion, or it could be some kind of attack. And so it's really important to understand that hazards aren't necessarily occurring in isolation. And again, the vulnerability is a function of the hazard. So it's really important to think about how those hazards are shaping which communities are vulnerable. And so we can go back to this understanding of how we think about vulnerability or which communities are most susceptible to impacts. And we see that for the most part, those communities that are very highly vulnerable traditionally to things like heat or hurricanes are also those who have been really impacted by the COVID-19 crisis. And however, it also changes. So for example, with the heat example I gave, we had that the very old and the very young were more susceptible to health impacts. But with the COVID-19 crisis, we're seeing really the very old experiencing the severe brunt of the COVID-19 impact. And so maybe that kind of shifts our understanding moving forward. And taking this understanding of how we frame risk, we can then move into the question of how does COVID-19 change how we adapt to climatic hazards? And I'm going to be using extreme heat as the example again, because that is what I look at in my work. But the important thing is to realize that this can go to other hazards as well. And there are traditional ways that cities have employed adaptations to extreme heat in the past that have been really successful. For example, they have employed cooling centers. And for those who don't know what that is, that's basically just a free space where somebody can go and rest for a couple of hours or for as long as they need that has air conditioning if they don't necessarily have access to a cool space. Another thing that's really common is people relying on natural amenities or other public spaces. For example, in Miami, I think a lot of us go to the beach or other water-related spots when it's hot out, but that could also be something like a very cool mall or shopping center. And we can see in the climate or in the COVID-19 crisis how this kind of shifts what adaptation options are available to us. We are required to socially distance, but that makes places like cooling centers or other public space-centered adaptations really difficult in that we are being asked to stay at home to prevent the spread. And so it really shifts which options are available to us. Another adaptation that's really important that cities have employed are social networks in which neighbors check on neighbors, people check on elderly folks. And this is something that's really an important adaptation because it relies on the capabilities that really exist within communities and those vibrant connections. And we can see in the COVID-19 crisis how this is really can be a difficult thing again when we think about social distancing. And finally, another major adaptation strategy is preparing the home through weatherization. And again, if your house is already weatherized, that's great. But if you don't have a weatherized house, then how are you going to get one at the time of COVID-19? You're going to need to get a crew into your house, which again is going to be really difficult in the time of social distancing. And so as we think about adaptations in relation to the COVID-19 crisis, we can see that it's going to become really difficult and we're going to have to start being creative. And further, we see that the COVID-19 crisis shifts extreme heat adaptations to home-centered solutions. And what this does is this really emphasizes and amplifies environmental and energy justice issues. And I think I really want to emphasize that it's not necessarily only extreme heat, but other hazards as well. We can see this really acutely with extreme heat, but it's not in isolation. And the reality is that this really kind of puts emphasis on how we can think of strategies that work for people in their homes so that they don't necessarily have to go out, so we can address the spread of COVID-19, but we can also address the problem of extreme heat and the health impacts that come with that. And so we have solutions that, first of all, we need to make sure that people can stay home. So are they able to afford their rent? And obviously we are dealing with a huge unemployment crisis caused from COVID-19. So that might become a huge adaptation strategy that can be very useful. And then even if people can't afford to stay in their home, so they have a steady home, are they able to keep that home safe? So for example, can they pay for their utility bills, which is a really important adaptation from the heat perspective, because can you pay for your AC, or can you afford your AC? Is your house cool enough? And we can see how this could have really significant ramifications if, for example, you had a child at home who is trying to learn. I think we can all empathize with somebody who's trying to learn in a hot space. And actually previous research has shown that trying to learn or be productive in spaces that is really hot is very difficult. And additionally, we could think about our water. If your water is cut off, how are you going to wash your hands? How are you going to stay hydrated? And so really thinking about the shift of where our spaces are in terms of what that means for our adaptation options is really something that's important with the COVID-19 crisis. But I think it really echoes moving forward how important we think about compound hazards and what that means for our adaptation options. And so that's just kind of a little overview of work I'm thinking about, but I'm really excited about it and would love to talk about it with you more. Here's my email. Please feel free to reach out to me. And I think right now is the question and answering session. So I will end it there.
Unmuted. So at this time, I'm going to ask everyone, continue to submit your questions into the Q&A at the bottom. I'm going to start, but if we don't have any time left, I think we'll probably go 5 to 10 minutes a little after 12:30. But we will, if we're not able to answer all the questions in the Q&A, we will be sending a follow-up email, hopefully being able to address all of those questions that were left unanswered. First, I'm going to start with a question that goes to Marybeth. This is from Patricia. Do human-caused factors impact climate change more or less than non-human-caused factors?
Thanks, Kelsey. And I did want to thank all of the participants today for joining us for our first Climate Cafe. So to address that question, the climate change that we've been seeing recently is predominantly from those human-caused factors. So both human-caused and natural variability do play a role in changing the global temperature, but natural causes like volcano eruptions or different amounts of solar forcing will change the temperature up and down a little bit, but over long periods like decades and centuries, that eventually evens out. But the unprecedented rise in temperature, and thinking back to those carbon dioxide and temperature curves that Ben showed in his presentation of these giant upward slopes, those are from the greenhouse gas emissions, which are human caused. So the climate change that we've been seeing is dominated by these human factors. Thanks for the question.
Great. Okay, so the next couple of questions go to Ben. So the first one is from Anitra. So I think this question is related to the CO2 pathways. And so the pathways that you had shown in your one slide, which one is associated with large-scale mitigation on our end? That's the first question.
Yeah, that's a great question. Both the 2-degree stabilization and the 1.5-degree stabilization curves correspond to huge reductions in CO2 emissions. The 1.5 curve suggests net zero emissions, or actually negative emissions, by about 2035, something like that, so in about 15 years. The other curves, of course, one corresponds to doing nothing, and one is sort of the current status, and then one more is current pledges. So it might include, for example, China's made a big pledge to reduce their emissions. So those are sort of the the baselines. But really, to achieve that 1.5 degrees, we need to be at net zero in about 15 years.
Great. Okay, so the next one's from Falk, also for Ben. Mauna Loa has a magma body at 3 to 4 kilometers from the NOAA observatory. Did anybody look at whether some of the CO2 could originate from the magma chamber?
Well, thanks for the question. I actually don't know the answer to that. The only way I can answer it is I just don't know. But one answer I would have is that if that effect were large, I would be skeptical, because the Mauna Loa time series is quite consistent with lots of other time series that we have around the globe, including all the way into the southern hemisphere. But something that should be looked at.
Okay, and the last one for Ben for now. What is the easiest, quickest thing the general public and governments can do to reduce emissions when we come out of COVID? Under normal conditions, is it realistic to expect emissions from surface transport and aviation to be dramatically reduced as they have been in the past few months?
Clearly, we're not keeping our reduced emissions going forward at this point in time. But I would say that I think there's been a bit of a cultural transformation in much of the world to recognize that we really don't need to go to the office as much as we've gone to the office. Both employers and employees are recognizing they can be really productive in a remote environment. And I hope we can expand on that. Less cars on the road, less CO2 emissions, and that can also translate into less flying around the country. You know, as scientists, we fly all over the place. Do we really need to fly to these meetings? Or maybe a lot of these meetings should be primarily virtual. So I think we're learning some important lessons. So I'm hopeful that we will be able to significantly reduce our emissions going forward for some of the lessons we've learned.
Okay, great. So moving on to Lynée, we have a question from Cheryl. How will biking as a mode of transportation and recreation be impacted by extreme heat? Early studies show bike ridership decreased at certain temperatures.
Yeah, great question. So relating specifically to the question about biking, I think this is true for a bunch of different adaptations that rely on personal preferences. And you're right that there has been previous research that's shown that people don't want to bike or walk when the weather is too hot or too cold or too rainy. And so relying on that as first a mitigation strategy to prevent people from emitting more greenhouse gases is going to be tricky. But also, as you mentioned, from the extreme heat perspective, as it gets hotter, as we move forward decades into the future, it's going to be really hard to rely on these kinds of adaptations if the climate is warming to the degree that we expect it will be. And then I think the other really thing that's interesting about this question is biking could be a really great adaptation actually in the time of COVID-19. It again reduces greenhouse gases, but it's something that people can do socially isolated and away from other people in a way that, for example, public transportation might be a little bit trickier. And it's also maybe more of an affordable solution. So people who maybe were relying on public transportation could afford something like biking much more easily than they could probably buy a car. And so it's a really important strategy when we think about how biking works for those two parts of it, but also adaptation strategies in general that rely on personal preferences that also address these compound hazards. So I think that's a really cool example you bring up.
Okay, great. So we have a couple questions that seem a little bit more open-ended. So for any and all of the panelists, one is from Lisa. What is an individual action that people can take to have a positive effect on climate change?
Jump in here is Amy. Can you hear me?
Yeah, go ahead.
Okay, so there's three things I think are really critical in terms of impacting climate change. One is getting involved. So we have a lot of local organizations that are addressing these issues, whether it's on the side like what Ben talked about of lowering emissions. Our city is actually trying to go carbon neutral within the next several decades, and we're actually on a path to do that. So local organizations working on carbon mitigation, but also recognizing that, as Ben pointed out, this slow, steady march of climate change, that we are faced with some inevitable climate changes, and we need to adapt our city in order to accommodate both the water and the heat and the storm surges. And we want to do that in a way that's fair, and it's in a way that we want. So there's a lot of different activities going on. I'll just mention the City of Miami's Climate Resilience Committee. I'm the chair of that, and we meet once a month. And all these kind of projects that come through, whether it's on reducing greenhouse gas emissions or adapting to inevitable climate change, are all discussed at that. And I would encourage you to participate. There are also Zoom meetings, so anybody can just, you can watch it on Miami TV, and you can provide public comments as well. So get involved locally, and there are also a lot of individual actions that you can take in order to reduce your own carbon footprint. A lot of people talk about reducing meat consumption, and choosing low carbon transportation whenever you can. Individual choices do make a difference collectively, and so I would say get involved, be proactive, and you can also get informed. I think coming to this kind of series is fabulous. I also want to echo what Marybeth said about it's thrilling to see how many participants you are here joining and hearing about our work. So please continue to come to the climate series, and follow us in our social media from the Rosenstiel School, and you can hear more about what we're working on. You can, again, come to the Climate Resilience Committees for the City of Miami. Happy to provide, to push that out in social media. So if you follow us, you can find out about that way. And there's also a lot of local organizations, non-governmental organizations that are very active. Miami Waterkeeper, Clio, Catalyst are three of the very active in this area on climate change impacts and equity. And we really need to all be working together to both reduce the causes of climate change and to adapt our city in a way that is fair and consistent with what we want.
Great, thank you, Amy. So we have a really interesting question from Jamal. How is social media and the spreadability of climate change news and updates impacting how research data is presented and packaged? So anybody can take this question if they have a feedback.
I can talk about this question a little bit, as it's something I think about a lot. So I'm really glad you asked it, Jamal. I think first from how is the media presenting climate change? As somebody who studies extreme heat, I think a lot of people, we're from Miami, we're like, extreme heat's not an issue, but the reality is it's primarily a low income issue. And we're not really hearing about it, and this is the case throughout the country, because it is a low income issue. And so I think the reality of you have to be critical in thinking about what the media is spreading is whose issue do they care about? And this is true, I think, for a lot of different hazards as well. And then I think the other issue you bring about, which is the data perspective. A lot of work that I do and my colleagues work on relies on publicly available data sets. And the reality is sometimes you can only do research if the data is available. And if we think about, for example, there is a lot of data available about climate change in California, but where's the data for Oklahoma, and where's the data for Georgia or other places that maybe are less climate forward? And so the reality is we're going to be doing work in those places like California, but not in other places that maybe need it equally. And so I think this question is so important because it really starts to think about some of the inequities within society in terms of who's presented in the media and whose questions are getting answered. So yeah, I have a lot of thoughts about this if you want to talk more about it.
I'm gonna read a question now from Ryan, and I believe this could go to Ben or Amy. Has anyone been able to successfully model one or more of the feedback mechanisms and their impacts on CO2 concentrations moving forward, particularly from the Arctic?
So I have to confess, I'm not 100% sure I understand the question fully, but we do have models that have a fairly comprehensive representation of all the feedback mechanisms. Certainly some are missing, but and in the Arctic, there's some really interesting work going on by a group. It's a Department of Energy supported group that actually out of New Mexico, that has been really looking at ecological and biophysical feedbacks in the Arctic, and using tools that really capture all the possible feedbacks for how changes in the climate system, if you think about Siberian melt and how that can contribute methane and trap CO2, and how that has a feedback on the warming in the Arctic. And so there is some really impressive modeling going forward. So I do think we're starting to get a handle on that stuff.
Okay, and I think we have time for maybe one more question, and this also goes to Ben, though I believe probably Amy could probably chime in. Could you talk about a few of the options that are available to help drain the greenhouse gas emissions?
Well, my knee-jerk reaction to that is, the first thing is we need to protect all our greenery in our rainforests. So we have enormous biological sinks of greenhouse gases that are natural sinks, and those are the rainforests around the world. We need to do everything we can to protect that greenery to make sure it continues to be robust sinks. So that's the first thing that jumps off the page for me. And again, just planting more trees. We just need to increase our biological sinks. I think is perhaps the most important thing. And I don't think we should be afraid of technology that we think can help us scrub CO2 from the atmosphere to some degree. And I think a lot of work is going on in that area also, geoengineering, if you will.
Great. So I would like to take the time to thank all the panelists for giving really good presentations and for answering these Q&As. And at this time, if there are any questions that we weren't able to address, again, we will be sending out a follow-up email. This video will also be available on our YouTube page. And lastly, we will be putting the links for Climate Cafe number 2 and 3 in the chat right now. So please register for the next couple of Climate Cafes, and we hope to see you there.
Thanks, everybody.
Thank you. Bye.
Thank you so much for doing this. Really, really appreciate it.
Well done.
Thank you for organizing. Well done. Well, great organization.
Good job.
Well done. Thank you, Deanna. Thank you, Sisam. Thank you, Marybeth. Everybody. Thank you.